Welcome to my chemistry assignment presentation by me, After. Today we'll be covering the differences between alkanes and alkenes, the different functional groups, and how to name compounds that contain these functional groups, and the difference between condensation polymers and addition polymers. Now let's start cracking. What are alkanes? Alkanes are the simplest carbon compound you can find, and they're composed of hydrogen and carbon. They are saturated, meaning they only contain single bonds, and this is the general formula. This denotes for every carbon atom you find, there's twice the number of hydrogens plus 2. This is the image of octane. Octane is the most popular and well-known alkane you can find, and is used in cars. Now there are three main types of alkanes. The types are different from each other according to the arrangement of carbon atoms. So for linear, the carbon atoms are arranged in a straight chain. In branched, you still have straight chains, but they're also side chains of atoms as well. And in cyclic, the carbon atoms are bonded together and they form a ring. When it comes to naming, there's two main rules. You first count the number of carbons and attach the suffix "ane." But you always remember, when you're counting the number of carbons, you always have to count it in Greek. If there are any branches you see, you always state the position of the branch in relation to the first carbon. As you can see here, this is an alkane and it contains 5 carbons here. You state the name of the carbon, a number of carbons, which is 5, which is pent, and then attach the suffix "ane", so this is pentane. For this one, you see a side chain, and you state the position of it in relation to the first carbon that's closest to it. So this is on the second carbon, and it's a methyl group. So it's 2-methyl, and there's 4 carbons here, butane. This is alkenes. Alkenes are very similar to alkanes, but the difference is that they contain a double bond. Now, you can see the difference it can make by looking at the general formula and comparing it to alkanes. This shows that for every carbon atom there's twice the number of hydrogens, whilst in alkanes it was plus 2. The three main types, and again, they're very similar towards alkanes, it's just dependent on the arrangement of carbon. So in linear, the carbons are arranged in a straight chain, branch there's side chains and parent chains, and in cyclic, the carbon atoms are arranged in a way they form a ring. The great thing about the double bond, the one here, it prevents the carbons from rotating. And what you have is that you have a phenomenon where you have structures which are the same with the same molecular formula, but different spatial arrangement of atoms. You have two types of isomers, cis and trans. Cis is when these groups here are on the same side, and trans is when they're on different sides. When it comes to naming, it's fairly simple. You state the number of carbons, obviously in Greek. You state the position in relation to the first carbon that's closest to it, and then the suffix "ene". Now, if the compound is an isomer, you always state whether it's cis and trans, and that's always placed in front of the name of the compound. You can see here, this is an alkene. There's 4 carbons here. The double bond is found on the second carbon, but you see these groups here on different sides. So this is trans but 2-ene. In this case, you have 1, 2, 3, 4, 5. 5 carbons, but this is pent 2-ene. However, these hydrogens are on the same side here, because it's always in the relation to the double bond. So this is cis pent 2-ene. So to summarize, really the difference is that alkanes are have single bonds, alkenes don't. This causes big ramifications in the sense that alkenes have a high saturation of hydrogens compared to alkenes, because the alkenes, the double bond, prevents the formation of other bonds that could be created with hydrogen that aren't made because the double bond is taking up all the potential bonds the carbon could make. Now, because of the double bond that the alkenes have, the alkenes are reactive, but also they can form isomers. But going back to the reactive point, you can actually show how reactive alkanes and alkenes are by conducting a bromine water test. When an alkane and an alkene are placed into bromine water, the alkane, the doesn't really affect the colour of the bromine water, which is brown, whilst alkene does. The reason why is because the alkenes, they contain double bonds, and they react with the bromine molecules. The double bonds break, and then they bind to the carbons, in relation to the carbon-bromine bond, and then that changes the colour. In the second part of the presentation, we're going over functional groups, and also naming and teaching you how to name compounds that contain these functional groups. Now, what are functional groups? They're a group of atoms that change organic molecules in important ways. That means it provides it with specific properties. For instance, famous functional groups are aldehydes, ketones, phenols, alcohols. And when it comes to naming them, it's fairly simple. The general is the name is composed of two components, the prefix and the suffix. The prefix is the number of carbon atoms in the parent chain that contain the group, and the suffix is dependent on the functional group in the compound. This table here shows the different suffixes that each functional group has. Here we have the alkyls. The alkyls are a functional group that is an alkane missing one hydrogen. These are fairly the rules here, but to make it easier for you, I'll show you. This is a hexane, and as you can see, the side chain is coming from a third carbon. Now, when it comes to naming this, you state the position of the alkyl group in relation to the first carbon that's closest to it, and then you state the number of carbon atoms in the parent chain, which is this. So this is 3-methyl hexane. In this example, it's a bit different in the sense that you have two functional groups in the compound. Now, there is an exceptional rule here, that certain functional groups have priority over others. Now, halogens, which is chlorine, will always have priority over alkyls. So in this case, you always count from the chlorine. So this is 1, chloro, third methyl, which is where you find the methyl group, and then you state the number of carbon atoms there are in the parent chain. There's 5, so this is 1 chloro, 3 methyl, pentane. When it comes to aldehydes, aldehydes are fairly simple. They contain a carbonyl group bonded with an R group and a hydrogen. When it comes to naming, the prefix is just essentially the number of carbons that contain the aldehyde. You don't need to state the position because the position of the aldehyde is always 1. When it comes to the suffix is al. So here, you have 6 carbons in the chain here, but it obviously has an aldehyde, so it's hexan al, so hexanol. Hydroxyls are the most famous functional group you can find. Normally compounds that contain hydroxyls we refer to as alcohols. Essentially, it's an R group bonded with an oxygen and a hydrogen. Now there's different types, and it's really dependent on the number of carbons that the carbon that's bonded with the hydroxyl molecule is bonded to. In primary alcohols, you have 1, secondary you have 2, and tertiary you have 3, as you can see here. When it comes to naming them, it's again fairly simple. First of all, you identify the prefix. That's the longest chain that contains the hydroxyl group. So that is, in this case, 6 carbons, so it's hexane. Then you state the position of the hydroxyl, which is 3, and then you state the suffix, which is ol. So this is hexane 3ol. This is a secondary alcohol because there's 2 carbon atoms attached to the carbon atom that's hydroxyl group is attached to. In this case, you have 4 carbon atoms here, but the hydroxyl group is attached to the first carbon, which is 1. So the suffix will be ol. So it's butan, 4 carbons, position of group, which is the first, and then ol, butan 1, ol. Ketones are like aldehydes, but they're not attached to the first carbon. So essentially, you have a carbonyl group, and the carbon is attached to 2 R groups as well. When it comes to stating the name, all you need to do is state the position of the ketone, as you can see here, in relation to the first carbon. Identify the prefix, which is the number of carbon atoms there are in the chain that contains the functional group, and then attach the suffix -one. So in this case, it's 2, 5 carbons, pentanone. So 2-pentanone. In this example, you have third carbon where you find the ketone, so it's 3. There's 6 carbons here, so it's hexane, and then the suffix -one, so 3-hexanone. Carboxylic acids, we name them just acids. Essentially what they are is a carbonyl group attached to a R group and a hydroxyl group. When it comes to naming them, it's fairly similar to aldehydes in the sense you don't need to state the position of the acid because it's attached to the first carbon. All you know about is the suffix and the number of carbons that the acid has in the chain. So in this case, you have 6 carbons, and then so it's hexane, and just attach the oic. And that's it. So you identify the prefix and oic. Prefix is the number of carbons. So the prefix here is 4 from butan, oic. When it comes to esters, essentially they are derived from a condensation reaction between alcohol and acid, and the group is composed of a carbonyl group, a carbon-oxygen single bond. The oxygen is attached to the R group, and the carbon is attached to the R group. It's fairly simple. For the alkyl, you just state the number of carbon atoms and then attach the suffix YL. For the acid derivative, you count the number of carbon atoms and then attach the suffix 08. So here you've got 3 carbons, propyl, and then you've got here 2 carbons, ethane 08. So this is propyl ethanoate. And using that same principle, you identify the alkyl, so this is methyl, and then identify the acid derivative, which is butan 08. Fairly simple. When it comes to amines, they're a bit like alcohols in the sense there's 3 main types, and the types are different according to the number of carbon atoms or R groups that are attached to the nitrogen. So in this case, for primary amines, you have 1 alkyl group. With secondary, you have 2 alkyl groups, and tertiary, you have 3 alkyl groups. When it comes to naming, you just identify the R group, which is the prefix, and then the suffix is amine. So here, you've got 3 carbons, propyl, and the suffix is amine. So it's propylamine. This is a primary amine, because you have 1 carbon attached to the nitrogen. Here, it's a secondary amine. You have 2 carbons attached to nitrogen. You just state the R groups, such as diethyl, and then the suffix amine. Phenyl groups are essentially a benzene group, but with 1 missing hydrogen that is replaced with an R group. And the naming is you just state the name, the prefix, which is phenyl, and then the R group is the suffix. In this case, it's phenylamine. In this case, phenyl, the prefix, and the suffix is ethene, because that's the R group. So this is phenylethene. In the third part of the presentation, we'll be covering the differences between addition polymers and condensation polymers. Now, what do these 2 images have in common? Nylon and PVC. They're both polymers, and polymers are essentially a sequence of subunits bonded to each other in a process known as polymerization. These units are referred to as monomers, and the process of polymerization has 2 types, addition and condensation. Addition polymerization is when alkenes, like this, or unsaturated monomers, conjoin together. In the process, a double bond is broken, and the monomers conjoin together covalently. In this reaction, you have ethene reacting to each other, forming polyethene. The double bond is broken, and the 2 monomers conjoin to each other, and these are covalent bonds here. This is the repeating unit, and this is the basic structural unit of the polymer. The number N represents the number of units that this polymer has. The monomer is enclosed in brackets, as you can see here. And when it comes to naming addition polymers, it's fairly simple. You first of all attach the prefix poly, and then the suffix is essentially the monomer, however, when the reactants are the same. If they're not, then it's just the product of that. In this example, I showed you vinyl chloride reacting with vinyl chloride producing polyvinyl chloride, or PVC. This is basically the polymer here, and this is the repeating unit. As you can see here, the monomer is enclosed in brackets, and the N is 4, and this is identified by there being 4 units here. Condensation polymerization is when monomers with different functional groups conjoin together. In the reaction, an ester bond is formed between the two polymers and water is produced. In this reaction, for instance, telepholytic acid reacts with ethane 1,2-diol. A hydroxyl group is removed from the acid and hydrogen from the alcohol, and water is produced. In here, this reaction produces ester, or in this case, polyester. Now, I've shown you the repeating unit of polyester here, and this bracket encloses the monomer of the polymer here, but the lines between it represent the possible bonds that could be formed with other monomers. The N represents the number of units the polymer has. Now, the difference between condensation polymers and addition polymers is the fact that condensation polymers, can break down fairly easy because they contain an ester bond, which can be hydrolyzed, meaning if you put water in this can be broken down. Thank you for listening to my presentation and hope you have a great day.